Schneid guy.
So now we're going to talk about the transport across capillaries. And so what we have drawn here is a capillary with some important pressures that are going to be dictating what direction fluid moves between the capillary and outside the capillary, which we call the interstitial space. So first, let's take a look at the hydrostatic pressure in the capillary. And we have down here a little guide to what these symbols stand for. So we have this pressure in the capillary, and you can see this pressure pushes fluid out. And we call the movement of fluid out of the capillary filtration. And you can see that there's another pressure that's outside the capillary in the interstitial space, abbreviated pi sub I, and that is the interstitial oncotic pressure. This pressure, think of it as pulling or drawing fluid towards it. So the combination of the PC and the pi I together are our forces of filtration. I also have an oncotic pressure in the capillary, pi sub C, and that is going to be drawing fluid into the capillary. I call that reabsorption, and the hydrostatic pressure in the interstitial space pushes fluid into the capillary, and together P sub I and pi sub C are our forces of reabsorption. And what is going to happen is when you balance all these forces together, we're going to have either net fluid entering the capillary, reabsorption, or net fluid leaving the capillary, which we call filtration. Now, if I look at Starling's law of ultrafiltration, which is going to put all this stuff together, we see that we have a capillary fluid movement on this side of the equal sign, and it's equal to these forces we put all together times what we call the K sub F, or filtration coefficient. The way to think about this is it's like conductance, because really this equation is like Ohm's law. We have a movement is equal to the conductance times a driving force. In this case, the driving force is grouping these different forces together and seeing where we end up. If I combine P sub C and pi sub I as my forces of filtration, and I subtract my P sub I and pi sub C as my forces of reabsorption, whatever forces are larger, that's going to dictate what direction ultimately the fluid is going to move. So if I end up with 0, I have no net movement of fluid. Now that could happen two ways. I could have my forces of filtration and reabsorption be equal to each other, or I could have the conductance or the filtration coefficient be equal to 0. Now, assuming I have some conductance, if the forces of filtration are larger than the forces of reabsorption, then I'm going to end up with a positive value. And that positive value is going to tell me that I have net filtration. And the reason why is the way we set this up is filtration minus reabsorption is how we're doing this equation. If, on the other hand, I end up with a negative value, that means the reabsorption forces are greater than the filtration forces, then I end up with net reabsorption. Now if I look at an example, I can group these forces a different way. I can group the pressures together. We can call that delta P, P sub C minus P sub I, and delta pi, pi sub C minus pi sub I. And we can see in this particular example, we don't need to memorize these numbers, but we'll just use them as an example, because on the y-axis we have pressure. On the arterial end versus the venous end, that's as we go along the capillary, that's the anatomy. I can look at the arterial end and say, well, if my delta P is 30, that means that the P sub C is larger. That's a force of filtration. And I have the pi sub C minus pi sub I is, let's make believe, we'll call it 17. Then that difference is going to be, in this particular example, a positive number. So I end up with a positive 13 times whatever that filtration coefficient is. So the key point is the positive number. My delta P is greater than the delta pi. And that means that my forces favoring filtration are greater than reabsorption. And you can see that I end up with green filtration as my net along the arterial end. Notice as I go down along the arterial end to the venous end, there's inherent resistance in the capillary, and that causes the pressure to fall. And as the pressure falls, it can fall below the difference in oncotic pressure here, and now the reabsorption forces are greater, and I have a little bit of reabsorption on the venous end. And this is a pretty standard way that it looks in a systemic capillary. I have filtration early on, and then some reabsorption at the venous end, but overall, even though I have some reabsorption on the venous end, in this case it ends up being, let's say, -7 times Kf, overall there's some net fluid leaking out of the systemic capillary.